Okay. So the big day is this Thursday. We'll have our first midterm. We'll spend maybe the second half of today's class on a review. Okay, so far I got only one message from one student with specific requests of something I should go through. But you can make your request as we start our review, all right? We still have something to finish from last time, which I intend to use the first half of the lecture to cover. That is the convexity part. It's probably the most abstract part of the course. So last class, we defined the concept of a convex set and some properties of it, right? And we made connection with the linear programming, and we show that the set of feasible solution is convex, and so is the feasible values. The set is also convex. Okay, so I think throughout the algorithm that we're talking about when we were using the simplex method, I kept saying that, oh, we're moving from one vertex to the other without any actual proof. Today you will have that as a confirmation. In the end, you will see what the simplex algorithm is really doing, okay, how it is searching for the answer. So as I said, I always say it's from one vertex to the other. So we need to properly introduce the concept of a vertex of a convex sheet and make a connection to the linear programming. All right, okay. So here I'll start with the definition of a vertex. Okay. A vertex, and in other literature, it's also called an extreme point. Okay. And this is defined only for convex set. Okay, so how do you define a vertex? So first we know this is a point in the set, right? So a point in the set that has some special property. Probably you already have a literal understanding of what is a vertex. It's some kind of a corner, a point, a pointy stuff. Okay. But we want to formulate it formally. Okay. So you know, if we have a convex set, if you have an interior point, we're not defining it rigorously, then you know you could find it as a linear combination of two other points in the set, and this is somewhere on the line segment. That will be like an interior point. Is that right? And for vertex, you cannot do that because it's squeezed to a corner. It doesn't have anything on the other side. Is that right? So that intuition will be what we will put it in this definition. We'll say that exactly you cannot represent it as a convex combination of 2 points in the set. Is that clear? I'll formulate it clearly. Okay. So I say that is not, okay, so not something I cannot do. So in principle, a convex combination, but it's enough to say it's the midpoint. So it's the half sum of 2 points. So let's say y plus z. So my point is x. Okay, I forgot to say it's okay. And then here, y, z, they are also in the set, and they are distinct. In S. Is that clear? You cannot find two distinct points in the set such that this point, the vertex here, is a convex combination. Is it clear, the definition? Okay, so maybe I could say a vertex X, but it's okay. Right. So let's take some examples of what is a vertex, just to get us familiar. So let's take a very, very simple one. Let's consider a one-dimensional set, which is just an interval. We know it's a convex set. For x taking value between a and b, where actual interval. So, OK, a less than b. So I have an interval here on the real line. So you'll see this is the line segment on the real line taking value from a to b. Intuitively looking at it, can you find any vertex? Do we see any point that is a vertex? Does it have some kind of a corner that it gets into? So how many vertices will we find for this? When you go to one extreme point, or you go to the other extreme point, right? OK, so here we have two vertices, x equals a and x equals b. Exactly the two endpoints of this interval. OK. And let's put up a proof. How do you prove it? I want you to prove it per definition. The definition says it's a vertex if you cannot express it as a half sum of two other distinct points. So I need to show that, let's say, let's prove it for x equals a, where x equals b will be totally similar. If you can prove that, the other is symmetric, right? So how do you show that? So the definition says it is vertex if you cannot do it like this. So I can show the following, which will be equivalent. If I show that if I can express this point as a half sum of two other points in my set, then those 2 points are not distinct. There's no way. Then I'm done. Is that clear? So that's the approach we will use. OK, so assume, or let's say a equals y plus z, a midpoint where y and z are both in my set, meaning I'll have the following: a less than y less than b, and z less than, z is between a and b, and so is y. That's my set. Is that OK? So just try to put up some argument here. OK, and then in particular, what do I have? In particular, I know y is bigger than a, and z is bigger than a. Is that right? So I can start from this assumption. A equals the sum of this. So a equals y plus z, half y, half z. So if I replace y with a, I would probably get something smaller if y is not a. Is that right? And if I replace z by a, I will probably get something smaller. So if I do that, I will have something, I'll have this inequality. I replace it. So because I have this inequality for y and z. Is that clear what I'm doing? I'm just arguing. And then I see these add up to be a, and it equals the left-hand side where I started it. So you show that a equals to bigger than and equals to a, and the two endpoints are the same. That means all along the way, you must have equal sign. Is that clear? So must have equal all the way. OK, meaning here you must have equal, and meaning y is a and z is a. That's the only value you can take to make it equal, right? So So I must have y equals z equals a. And they're not distinct. Okay, so not distinct. Okay, so that's how you show that is a vertex. Is that clear? All right, and the second example is we're not going into a detailed proof. If you want to be challenged, you can go ahead and form your argument. We'll just look at it. So let's say if I have a square, I can formulate my square, two-dimensional square, as a unit square from 0 to 1, 0 to 1. So you just have a square like that. And there's the origin. So can we find any vertices? How many of them? Where they are? Any suggestion? Do you think that's a vertex? Is it clear to everyone? If I want it to be the midpoint of any line segment, the segment cannot be completely in the domain. Is that right? So actually we found 4 of them in the corner. They are vertices. And so let me ask you, how about this point here? Can that be a vertex? If it is not, can you show me which part of the definition it does not satisfy? What's giving away that that is not a vertex? Can I express this as the midpoint of 2 distinct points in the set? Yeah, take this and this. That's the midpoint. Is that right? So that is not a vertex. Okay? So for this one, we found 4 vertices. They're just the natural corners of these polygonal shape. Actually, triangle will have 3. And if you have a hexagon, then you will have 6. Is that right? Any convex polygonal shape will have number of vertices equal to number of sides. Okay? All right. The next example, so example 3, we will visit the disk. Okay? So the unit disk, x, y, x squared plus y squared less than 1. Okay, that's just the definition. And I'm just going to draw a disk. Okay, pretend that's a nice disk. Okay, is that good enough? Unit disk border is a circle and centered at the origin. Do we find any vertices here? Are there any? How many? So what is the definition of a vertex? That is, a point cannot be represented as a midpoint of any 2 points, right? So do we find any? Well, for sure, any interior point is no good. What about a point on the boundary, on the circle? Does it satisfy the definition of this vertex? We think so, don't we? If you draw any line segment through that, the segment cannot be completely in the set, isn't it? Is that clear? So we actually have infinitely many vertices. Any point on the boundary is a vertex from visual inspection. Is that right? Do we agree? So any point on the boundary is a vertex point from visual inspection. So I will challenge you, if you're curious, would you be able to formulate a formal proof per definition to show that it is? Okay, just not homework, just for you to entertain if you want. Okay, so now we need to go back to linear programming to connect these concepts in the simplex algorithm that we're using. So I kept saying the simplex algorithm is starting at a vertex and then move to another vertex and just checking. Now we're going to officially show that those basic feasible solution is a vertex. Okay, so here's the theorem. I don't know which number it is. Okay, I have a 9 on my notes. Okay, so for our linear programming problem, a point in the feasible region is a vertex. So this is a very strong statement. Well, let me put it up first. If and only if, okay, that means equivalent. It's a basic feasible solution for some canonical form of the same linear programming. Okay, so that's exactly what we use in the simplex algorithm. That is, we put it in canonical form and we find a basic feasible solution, and then we try to move to another basic feasible solution. Is that right? So this theorem is telling you that that basic feasible solution is a vertex in your feasible region. You're just moving from corner to corner. Okay, so if and only if, that's a very strong statement. It says that a basic feasible solution is a vertex. And if you shall have a vertex, it shall be able to express as a basic feasible solution. Okay, so the second one is much harder to prove. So what I will present to you is the proof from B to A. It's okay? The other one, in some textbook, they have it. You can read it. It involves some epsilon stuff, which we have not covered. Okay, we don't want to go in there. Okay, so I will only prove the following. That is a feasible basic solution is a vertex per definition. Okay? The converse is too complicated. I will not do that. Okay. So per definition. So let's see. Let's set up some. Let's put the problem in the setting. So if I have a feasible, basic feasible solution, then it is a basic solution of some canonical form. I could rearrange the indices such that the basic variables have small index. The non-basic variables are the ones with the big indices. I can always do that, just rearrange them. Okay. So without loss of generality, I can consider the following LP in canonical form. Okay. Consider, okay, in the canonical form. So, okay, with the solution. So as I said, I will move the B1, B2. Those are the basic variables. They have small indices, right? And the one with large indices are non-basic ones. They will be 0. Is that clear? The basic solution takes the right-hand side for the basic variables and 0 for the non-basic ones. I can rearrange and present it like this. So let's call this X. And I want to show that that is a vertex, okay, for the feasible region. So per definition, we'll follow, again, a similar approach for the simplest problem we proved. So what I will do will be, I will assume that this can be written as the midpoint of two other feasible solutions. And then I will conclude that those two have to be the same. They're not distinct. Is that clear? That will be my approach. Okay, so let's do that. So assume I have two other solutions. Let's call it x tilde, x bar. They are just feasible solutions, not basic. Okay, let's write the element of it out. So I'll have x tilde 1 all the way to x tilde n. I have n of them, and then x bar is the same. Okay, with this component, and I say that I assume that my solution x is a midpoint, so half x tilde plus x bar. Assume that. Can I do that? Okay, that's, and then I will eventually show x tilde must equal to x bar, equal to x. Okay, that's my goal. Okay. So what will be this sum then, if I add them up? I know this right-hand side will be a vector where each element of it, if I look at the ith element, it will be just x tilde I plus x bar I divided by 2. Is that right? You just add up each element. And this shall equal x, which we know. That's our basic solution. Where we know that the last n minus n position must be 0, which means the last n minus n position for this sum as a vector must be 0. Is that clear? So now let's check. Consider the last n. Okay, let's say consider elements with index from m plus 1 to m, I from m plus 1 to m. And then we must have the following. We must have 0 equals half x tilde I plus x bar I from m plus 1 all the way to n. Is that right? That's just by the way I set it up, right? If this plus that half has all these as its element and this equals x, then those must be 0. Is that right? And also, we have a further assumption that these are feasible solutions. What does that mean? That means all these are non-negative. Is that right? So we also have, okay, let me go up here. We also have xi tilde bigger than equal 0, xi bar bigger than equal 0. If none of this is negative and they add up to be 0, what do they have to be? All zeros. Agree? Then we'll have xi tilde equals xi bar equals 0. Okay? For all these I from m plus 1 to n. Is that clear? So these two are not just random feasible solutions. They are feasible solutions where all the non-basic variables are 0. So think of it in the canonical form where you set all the non-basic variables to be 0. What must the basic variable take as value? The right-hand side value. Is that right? You just have this diagonal form, isn't it? So there's only one. So you must conclude that xi tilde will equal to xi bar equals bi for all the basic variables. Is that right? You can just write out the canonical form and be conform. And then these two vectors, these 2 points are the same. Not only are they the same, they exactly equal to that x, the basic solution. So it has to be a vertex. Is that clear? The proof? So x is a vertex. Okay, so at least we proved that the basic feasible solutions that we have been using in the simplex algorithm are all vertex points of the convex region, of your feasible region. Okay? Yeah. So in the simplex algorithm, thinking back what we did, we start from a basic feasible solution, which now we know is a vertex of the feasible region. And then we did pivoting, and we exchange one basic variable with the other, and we move to another basic feasible solution. So we are moving from one vertex to another in one pivot step, right? But not just randomly moving, but this move is particular. So because we are switching just one basic variables, right? We're not jumping over, okay? I know during the algorithm, I kept saying we go along the edge and move to a neighboring vertex. Okay, now we will prove that. I'll give you a formal definition of what I mean by an edge of a convex region, and we'll show you that we're exactly moving along the edge. All right? So let's define an edge. Okay, what is an edge? So is a line connecting two vertices. Okay, but that's not enough, because, you know, going back to the unit square, if I pick these two vertices and then I connect a line through it, well, intuitively, whatever, you know, that's not an edge. That's going into the region. Is that right? And in this graph, we see that this is an edge. It's like on the boundary, right? So think of a point over here and a point over there. How are they different? What properties are essentially different of 2 points that's on the segment connecting two vertices in these two situations? Think of this point here, which we are thinking it's not an edge. So this point is not on an edge, and that is not an edge. You can draw any line segment. You can have many of them that's not on the same line, that this point is a midpoint. Is that right? Do you see? I can draw this line segment, and that's midpoint of those two, and those two are not on my line segment. While this one, I say it's an edge. Why? Well, because if you find two other points where this one is a midpoint, like this, so these 2 points, that one is a midpoint, all those 3 are in my set, but now you see those 2 points are on the same edge, only on the same edge. That can serve. Is that clear? So that is very different, right? So this is exactly the way we're going to formulate our definition, okay? So it's just not, it's a line connecting two vertices, but not any of them. It's the one with some special property. Okay, so let's formulate. So if I pick any point, x, on an edge, it can be written as x, the midpoint of other two y plus z half, okay? Not for any y and z, only, so this is important, I'm saying only for, should I call it yz? Okay, yz on the, let's call it, okay, yz, whatever, on the same edge and same segment edge. Okay, it's clear. So this is just a more wordy, a more concise way of defining what I just said there. Okay, so it's an edge. Then it can be represented as a linear combination of two other points. The two other points must be exactly on the same edge. No other way. Is that clear? The definition? Right. Now we want to prove that in the simplex algorithm, where we move from one basic solution to the other by changing one basic variable, you are exactly going along an edge. Okay? So here's the last theorem, Theorem 10 is my index. Okay, so now we're talking about linear programming. So two vertices or two basic solutions where we have there in the linear programming problem, where only one basic variable is changed. So not any vertices, that two special ones where you switch one basic variable with the other, and we claim that this is an edge. Okay? Edge of the convex set of feasible region. That's understood. Is that clear what I'm claiming? I want to show we are going along edges. Okay. Let's try to prove it. It's pretty similar to the proof in Theorem 9 that we show it's a vertex. Okay, so we want to show that this is an edge per definition. Okay. So I have two vertices in my linear programming problem where only one basic variable is changed. So again, I can rearrange indices such that for one variable, the basic, for one solution, the basic variable are the first m, and for the other one, I take one out and add one in. Okay, so it's general. I did not lose any generosity by assuming that. So so just say I'm not writing down by possibly rearranging indexes. I can just consider the following case, which is general. So consider two feasible basic solutions. I call it x bar and x tilde in the following form. So for x bar, I have the first m variable as my basic, right? And after that, these are all non-basic, and they are set to be 0. And then x tilde is another basic solution where I switched x1 with xm plus 1. Just, you did one pivot. So now this is 0, but then now from x2 all the way to, I still have x xm, and I'm bringing in xm plus 1 as a basic variable. So I switched 1, okay? And the rest is 0. Is it clear what I'm setting up? Okay, and this is general because I can always do it in any situation, okay? Okay, so, and then from the previous theorem, we know these two are two vertices. Okay, now I'm going to connect them, and I'm going to pick a point along. So let x now be a point on the segment from x bar, connecting x bar to x tilde. So what does it mean? So if you have 2 points and you connect them and you find a point along the segment, that is called, all these points can be written as a convex combination of those two, right? You have this parameterized formula for the line. So that means I can express x as a convex combination of x bar and x tilde, some form, okay? So that means for some t, that's our parameter, where t lies between 0 and 1, we have the following. That is, x is a convex combination of the other two. You can always do that. Okay, if that is the case, and then let's do this convex combination. So you will be adding up the elements in the same position by the same combination. And in particular, the last, this group of elements, they're 0 in both x and x bar and x tilde. After adding them up, you will still have 0, right? So my x must have the following form. X will equal to x1, let's write it out, x2, all the way to xm plus 1. So the first m plus 1 could be non-zero, but the others would all be 0. Is that right? That's called the form, a star form. Okay? Now, so there is this little step here that I will put up, and I will leave that as a homework for you to work on. So we have the following. I know I have 2 things. X is a feasible solution, okay? Which is kind of obvious because we already know the set is convex, right? But in the homework, I will ask you to prove it in the setting of linear programming. Just prove it in detail to say that any linear combination of 2 vertices like this is in the set. It gives you a feasible solution, okay? And furthermore, I claim that any feasible solution in the form star is on the segment. Okay, so, and this I will give as a problem in homework 6, so for you to practice your proving skill. All right? Okay, with that, and now what do we need to show? Now we need to show it by definition. We need to show that this point x here can be expressed only as a midpoint of 2 other points. They must be on the same edge. Is that right? And then this is the edge. That's per definition. So I need to prove that. Okay, so let's put 2 other points. Let's assume x equals a midpoint of some other point. Okay, I'm keep putting more things. So x prime is another point, x double prime is another point. Where these are feasible solutions. Okay, so let me write it. So x prime, if you write out the components, is x prime 1 all the way to x prime n, and x double prime is x double prime 1, x double prime n. Okay, these are feasible solutions. What I need to show is I need to show that they must be on the same line segment. Then that's an edge. Is that right? Okay, so let's see if we can tie up that argument. Okay, so by our assumption, x is the sum, is the midpoint of x prime and x double prime. Then if I write out the component of it, then I know the first component will be adding up the first component from each and take midpoint and so on and so forth. And the last one will be xn double prime half. So x must take that form if it's a linear combination of midpoint of these x prime and x double prime, right? And then we also know that x is in this form star, that is the position I from m plus 2 to n, x is 0, right? So use that. Let's use that. So I know for the following. Then I know that for I from m plus 2 to n, we have xi prime, xi double prime half must be 0. And x prime, x double prime are all non-negative. The same argument goes again. What do they have to be? If these are non-negative and they add up to be 0, they must be 0. Is that right? xi prime, xi double prime, they are all 0 for all those positions, m plus 2 to n. It's okay? Which means those two will have x prime and x double prime will have the last n minus m minus 1 position to be all 0. Here I must have it to be all 0, meaning they are in the form star. Is that right? With the 0 here. Okay? And you see where we're going. So x prime, x double prime has 0. Okay, that I already wrote. Okay, they are in the form star. So then we know x prime, x double prime, they must be on the segment connecting x bar to x tilde. Okay, and that is exactly our definition for an edge. So the situation being described in this theorem is exactly the situation where we pivot. Is that right? The purpose of pivot choose one place to pivot is exactly to switch one basic variable with one other, one and only. And with this theorem, we see that you are now moving from one vertex along an edge to another in one step of pivot. Is that clear? So I will put that final thing as a corollary, and which is obvious. Right. Okay, so let's formulate this, what I just said. So in the simplex method, the one we have been using, I talk about each pivot. What do you do at a pivot step? What it does is that it just moves from one feasible solution to another. So it moves the basic feasible solution from one vertex. We know they are vertex, right? And it's just not really randomly moving, and it actually going along an edge, right, to the next one. Okay, so that's what one pivot step will do. So move from one vertex to a neighboring one that is connected by through an edge. Is that okay? Any questions? We're okay? I know the past week or two has been very abstract, and probably this is the last. Well, there's the duality theorem, which is conceptual also, but okay, so if you like more hands-on stuff, there's good news. So on Thursday we'll have an exam, and then the Tuesday next week when we come back, we will enter the chapter where we'll learn how to use Excel to do the minimization or maximization problem. There would be like which place you click, where you put plus, minus, and then you click solve, and it runs for you without knowing what's going on. Just know where to put what, right? So totally different class will come next Tuesday. Is it okay? Any questions regarding what we had today? Okay, so, and that's that. And now we move to something that probably what you came here for, the review of the exam. Everyone has seen the review sheet on Angel Canvas. The angels should not be whispered. Okay, so the exam as I have it right now has 7 problems. You have 75 minutes. You have about 10 minutes to solve each, okay? And some student asked me about, can we use the LP assistant? What about the pivoting process and so on? So there are no problems that requires assistant of LP assistant, okay? I will check if you are able to perform the pivoting process, but those problems shall be done by one pivot and with totally okay numbers, not nasty numbers. If you make a mistake, it can turn into a lengthy one, all right? If you did it right, it's clear, one step, you're finished, okay? So don't worry about it. And we will be in the other room where you have all the computer screens in front of you. So this is a closed book exam, no notes, no textbook, not allowed. So no logging into the computer is allowed. You just bring yourself here and you do it, all right? So I want to say that There are no nasty numbers, no lengthy computation. The problems more are like conceptual. If you understood the things that we have been learning, you see a problem, you will know what you have to do. You can finish it in half time. But if the concept is unclear to you, then you can get stuck for a long time. Then I don't know how long it will take. All right? You have 10 minutes, and I'd expect like 5-6 minutes, you should be able to finish each problem. It should be all straightforward. Is that okay? So I will bring scrap paper, but you should bring something to write. It's an exam. You should bring your Penn State ID. I will have to check it by regulation. And okay, so it's a joke. Don't take it personally. Student will ask him, what do I bring for the exam? I would say that depends on your level of confidence, right? If you are confident, you bring a pen, whatever I put down, correct, no change, I'm done. If you are a bit less confident, maybe you think that's too dashy, and then bring a pencil and an eraser. Is that okay? And then if you really have no confidence at all, last strategy, you can bring a big eraser. You can erase the problems. You know, there are these erasers, huge, and it says, for big mistakes. I have one in my office. I can bring it with me if someone wants to borrow. Okay, so I will bring scrap paper so you don't have to worry about it. And one thing important I have to say, I will give extra office hours, okay? I will try to review a little bit today, but maybe not too much. You have questions, I'll be available most of the time from now on until the exam. So extra office hours. Okay, so today I put 2 to 3 this afternoon. You can come. And Wednesday, tomorrow, I can put a morning session and put an afternoon session. Is that okay? I do have something at lunch. So 9 to 10. I have to leave at 10:15, so I can push a bit. And then in the afternoon, let's put a different time. That's what I put in the other class. So if that time doesn't work for you, it's half an hour switched. And then we normally have a Thursday office hour. Can I say for this week, I cancel it? I don't think anyone will come after the exam. Well, can I officially announce I cancel it? So canceled, just for this week, okay? We'll have all 3 for today and for tomorrow. Will that be okay? Okay. Now, I did send an email to everyone asking any specific thing you want me to cover. I got only 1 reply. So that person will get his wish fulfilled. I'll cover what he wants me to cover, unless you make your request now. So let me tell you what I did in the other class. We did a modeling problem, a transportation problem. There was a not-so-friendly homework in that direction that got us a bit confused. And another example is the one that rewrites a problem into standard form with the absolute value sign in the original constraint. How do you handle that? Would that be okay? We do that, or you want something else? Okay, then is that okay? Then I will do that. Okay, so the first one is a modeling one. I'm going to take transportation model, problem set 2.4, problem 2, part A. Is that okay? We'll do that. So 2.4.2a. And part B is more complicated. I don't think we'll get that complicated. So here you want to transport stuff. I think there's a mistake in the problem, or the wording is not precise. So you have basically two warehouses. So let's list it in the warehouses, east and west. Can I call it 1 and 2? East and west. I'll just label it. And then I have outlets. I label them 1, 2, 3, 4, where you want to ship your goods from warehouse, distribute them to the outlet where you can sell, right? And what I put here is the shipping cost, okay, unit price. So 20, 45, 16. These are numbers, you know. Okay, and that's that. And then each warehouse has some requirement that you need to ship. It wants to have so many. So requirement. Okay, let me put down those numbers. So how many units it wants? 300, 350, 400, 450. Now here, the problem is not well stated. What do you mean by requirement? It didn't say. Does it mean it has to be at least that many, or it requires exactly that many? Okay, my problem will be clearly stated, all right? So assuming that it wants exactly those numbers, okay? And then there is a mistake in the problem. So each warehouse has some cases stored. So storage. Okay, so for the first warehouse in the problem, it says it has 600, and second warehouse has 1,000. And you want to ship those to 4 outlets. If the number's exact, and then these need to be all shipped, if that's what you require, then you add these up. It must equal to you what you add these up, right? And right now you see it's not the same. Okay, so I'm going to change the number. Let's make this the exact one. If it's not exact, then you have to change equal sign into inequality in your model. Is that clear? Well, we can talk about that. Let's say we want equal sign. Let's say everything in the storage warehouse must be shipped to the outlets. Then the sum here and the sum here, they must equal, all right? And actually, you will have a redundancy in your model, but that's, you don't need to deal with that. You just need to set it up. Okay, so what variables will you define? You actually need to define a bunch of them. X, I, J. Let's say I is 1, 2. J is 1, 2, 3, 4. You need to write this down clearly for me to read to see what you mean by that. Okay? Okay, so define this to be, so this will be the unit, that's your schedule, right? The unit, how many from warehouse I is going to outlet J. Is that right? So be the amount of shipment from warehouse I to outlet J. Okay. Is that what you were thinking if you would do this? So how do you define a cost function? So that's the thing you need to define, and you know that is the thing you need to minimize. Is that right? So you write minimize the following. So how do I figure out the total cost for these shipping? So if I ship X11 unit from warehouse 1 to 1, and the cost for each unit is 20 unit of money, how much would that cost me? Is the product of those two. Is that right? 20 times that. So you just know you have to write this out. So 20 will be multiplied on x11 to figure out how much that will cost you. Once you figure out one position, all the others are the same, similar, and then you add them all up. Is that clear? So add up 16, x12, 30, x13, 20, x14. Let me write the 4 nicely. Plus, then from warehouse number 2, 45, x21, 39, x22, 50, x23, and 44, x24. Okay, so that's what you have to minimize. And then let's find the constraint. Subject to. So the constraints would come from two things. One is to the warehouse. Okay, sorry. From the warehouse, I have only 500 in warehouse 1. I cannot ship more than that, and they have to be exactly all shipped. Is that right? So how many will be shipped out of warehouse 1? Well, you ship that many to outlet 1, x11, x12 to outlet 2, meaning you have to add all the x's in here. Is that right? So let's write storage constraint caused by that. So I will have x11 plus x12 plus x13 plus x14. They must add up to 500. Is that clear? And then the second one, similar. All the x you have here, you add up in this direction must meet that number. So x21, x22, x23, x24, they add up to be 1,000. Is that okay? Okay, and then you also have the requirement. Because you are only going to send 300 to outlet number 1. So the total amount you send there will be x11 plus x21. Is that right? That must be exactly 300. That's for outlet 1. And you go through all of them. So you have x12, x22 is 350, x13, x23. If you add that up, I get 400. And you have x14, x24, that is 450. So this is the other bunch of your constraints. And then I tell you, one of these equations is redundant. You can remove any one of them, but you don't have to. When you set up the model, just set up as it is stated. All right? We're not detecting redundancy here. So what you must not forget that I have not written, the positivity. Is that right? And you have to, that's important. Xij bigger than equal to 0, I from 1, 2, j 1, 2, 3, 4. Okay? And that will be a perfect answer, losing no points. If you don't write this one, I will be forced to take away some points because it's important, the non-negativity. Is that clear? All right, so that is one. Another example dealing with how to rewrite into standard form with tricky constraints. In particular, want to do one with the absolute value. Okay, we're not solving the problem here. We want to, okay, so consider the following. Let's say minimize let's say x1 plus x2, just fake. So it's the condition that I have to redo. So let's do a simple condition. x1 absolute value less than 3, and x2 is -1. That's a very strange condition. And they're unrestricted. How do you rewrite this in standard form, in the linear programming setting? These are the worst case. Okay. So now for the absolute value, you have to break it up into two inequalities. Is that right? So this one, you will break it up as x1 less than 3 and x1 bigger than -3. Okay? Okay, so let's deal with this unrestricted situation first. And we see both x1 and x2 are not restricted. They can be negative. So you have to deal with that. So I need to introduce artificial variables. Is that right? So artificial variables, that's what we call it. So I will write x1 to be x1 prime minus x1 double prime. I introduce two of these. And x2 will be x2 prime minus x2 double prime. And now these are all non-negative. I can do that, right? And then I have to rewrite my problem. I take a step. So minimize. First, I get rid of these, right? So minimize. So x1 now is x1 prime minus x1 double prime. And then x2 prime minus x2 double prime. Okay? Yeah, question?
Why are you doing artificial variables instead of slack variables?
Slack is when you have less than, bigger than, equal sign. Those what you add are called slack. This one, break x into as the difference between two other, this is called artificial. This artificial variable is different from the other artificial variable at the end when we add it to make it canonical form. It's another artificial variable. Okay? I know, is that the confusion?
Yeah.
Yeah, okay. So we have two different types of artificial variables here, all right? So this is not the same. Okay, and then I have x1 less than 3, then I have x1 prime, x1 double prime less than 3. That's the first one. And then x1 prime minus x1 double prime shall be bigger than -3. And the third one is x2 prime minus x2 double prime equals -1. That's my constraint. And then all of them now are positive. Is that right? It's not in standard form yet, but I got rid of those absolute value or unrestricted situation. Now you can add slack variables. Is that right? Now what you do, add slack to change the inequality into equal sign. Is that okay? So now you can add slack variables. Okay, so for the first one, let's say I will be adding x3 as my slack. For the second inequality, I will be adding x4 as my slack. Okay, so let me rewrite the constraints. Will that be okay? I'll just write the constraints. So the first one will be x1 prime, x1 double prime. So this is how I remember it. It says less than equal. If I want to make it equal, I need to make the left-hand side a bit bigger. So it's plus. Is that clear? That will be equal 3. And then the second one, x1 prime minus x1 double prime. Now it's bigger than equal, so I need to take away something on the left to make it equal, right? So you'll be minus x4. That will be -3. Is that okay? And the last one is unchanged because it's already equal sign. So x2 prime, x2 double, that will be -1. Don't forget, don't lose that automatic point. That is, list all your variable here and say that they are non-negative. Now this becomes a standard form. Is that clear? Yeah. Any questions? You have all those office hours, all right? I will be there. Just come and ask. Okay. If you don't come, wish you good luck on Thursday.